This. Yes, this is why I slow this distribution down and take it at this speed right now. Let's jump over this one for a second. I got a reason for this. Let's jump right to 2. What's the chance they're both girls? What do you think, friends? Jen, go for it. 0.81. Why 0.81? I love that because you're saying that's the chance Bertha's a girl. And that's the chance Nancy's a girl. So the chance they're both girls is 0.81. And I got no problem with that whatsoever. That's got to be true. Now, let's do this next one 2 different ways. If this is the probability, of both being girls, and this is the probability of both being boys, what number has to go here for the chance of... This is a good review for your exam on Wednesday. What number has to go here? Well, that's 81%, that's 1%, that's 82% altogether. It has to be 18%, doesn't it? So what I'm going to do is I'm going to put that number in right here, 18%. We're going to put it in orange, we're going to come back to it. Could we calculate it? Well, I think this is where the kind of consternation is happening. Because if you have to have one girl and one boy, how are we going to calculate that? What do you think? Give me some ideas.
Oh, what?
Give me some ideas. Go ahead, Jada.
Wait, no, because it doesn't wait.
Say it.
Like the boy and the girl. One of each together?
One of each. It's got to be one of each, right? One girl, one boy. So let's multiply some stuff, right?
That's what I was thinking.
Let's multiply. What should we multiply?
0.9 times.
0.9 times 0.1?
Yeah, but that's 0.09.
Okay, check this out. When you do 0.9 times 0.1, you get 0.09, which isn't enough, is it? As a matter of fact, not only is it...
0.9.
Say that again.
Times 0.9.
Check this out. This is 0.09, correct?
Yeah.
Which is not enough. It needs to be 0.18. This is actually, it's exactly half as big as it should be. Why would it be exactly half as big as it should be?
Oh, because there's 2 chickens.
Because there are 2 birds. And when you say 0.9.1, can I insert something really quickly here? This is the Bertha column. And this is the Nancy column. Is that okay if I do that real quick?
Yeah.
Bertha's a boy, Nancy's a boy. There's no other way to look at that. That's like rolling snake eyes on dice. You got double ones.
Yeah.
Bertha's a girl, Nancy's a girl.
Yeah.
There's no other way of looking at that. Bertha's a boy, Bertha's a girl, Nancy's a boy. Isn't there another possibility?
Yeah.
Couldn't Bertha be the boy and Nancy be the girl?
Yeah.
So, mathematically, we've got to say that. Let's say it. Ready? This is the challenging one. Bertha's a girl and Nancy's a boy.
One chance.
Plus y, because what word goes in there?
One is a boy.
Or Bertha is the boy and Nancy's the girl. That's why you were missing probabilities, because when you get into the middle of these, things get really interesting. You have to start mixing and matching, because when they're not all or none or all, I guess we look at it that way, you have to start playing with the individual pieces and where they could be. So yeah, either Bertha is the girl and Nancy's the boy, or Bertha's the boy and Nancy's the girl. That's where your extra 0.09 comes from.
The column stuff really helps.
It does.
More.
It does. And the problem with not using the columns is you get lost. There's a formula for this. I'm never going to show it to you. Well, I shouldn't say that. I might show it to you eventually, if you want to see it. But I love this way. This way plus technology is the way to go. Does that sound to 100%?
Yep.
Sure does. We picked up our extra 18%, 9% and 9%. So in other words, there's a 1% chance they're both boys. There's an 81% chance they're both girls. There's a 9% chance Bertha's a girl and Nancy's a boy. And there's another 9% chance that you got the flip-flop. Bertha's the boy and Nancy's the girl.
That's beautiful.
Oh, I agree. This is the mathematics of what's going on with those likelihoods. So another way of looking at this, and this is the shortcut way of looking at it, I'm gonna erase a little bit, it's okay with you guys. Numerically, this and this are exactly the same, correct? So what mathematically we could do, if you want to keep it clean, is just put a 2 out in front, double it, does that make sense?
Yeah.
0.18, 18%. Mathematically, it's equivalent. Fair-ish, believable? Good-ish.
So with 3 birds, would you put 3?
Let's come to 3 birds. Just a second, Jada. Hold that thought. Give me 5 minutes.
Okay.
I got a bigger question. A bigger question first. What's the average number of girls
1.8.
per 2 birds? Per 2 birds. So this is per 1 bird. So over here, what's the average number of girls? I should put it in arrow, not equals, not arrow. So I heard a vote for 1.8. Tell me how you got that, Haley.
I times and added.
Awesome! You can once again, you can always, my friends, you can always go this times this, plus this, times this, plus this, times this. And if you do that, look what you get. You get 0 times that, that cancels. That's just 0. 1 times 0.18 is 0.18. So right now, this gives you 0.18 of a girl. So roughly 20% of a girl, ish, 18% of a girl. And you've got 2 times this. That's 1.62. 1.62 plus 0.18 gives you 1.8 girls per 2 birds. Does this ratio look familiar?
Mm-hmm.
Was 1.8 girls per 2 birds? Does that ratio look familiar? If you divide that out, what do you get?
Yeah, that number.
You get 0.9 girls per 1 bird. You get 9 girls per 10 birds. It's the same ratio. Because on average, it's going to smooth out over time. It has to go to that average of 90%. It can't not, if that makes sense. It has to on average. Assuming the guy's 90% was right. Now, I want to notice a couple things. When we went from, you know what, I'm not going to notice this yet. Let's notice after we do the flock of 3. The 3 flock is the one that Jade is asking about, and I think it'll be a little more obvious when we get to that flock of 3. Is everybody solid with why we don't have to do any multiplication in front of the all boys and the all girls? You don't have to put this 2 in front of these guys?
No, because it's the second power.
Exactly, it's the second, because there's no other way of doing it, right? There's no other way. If Bertha's a boy and Nancy's a boy, there's absolutely no way of any other thing happening. You can't switch them.
Yeah.
Cool? All right, let's build the next flock. Let's go. We're going to add Marge into the mix. We now got the Orpington. Okay, I got the Orpington now. So we're going to replicate the exact same flock, except now I set Max back in to buy a 3rd bird. We're still charging? Ish. Looks like we're getting there. Actually. Okay, yeah, we're good. Okay, flock number 3. Flock number 3. Okay, we're by 3 birds. 3 birds. I want to know on average how many I got, the average number of girls per 3. But I also want to build a distribution. Chances are you can figure out what the average number of birds has to be, can't you? You can probably figure it out by now. You're seeing the pattern. You're seeing the pattern. Every time we add a bird, we basically add 0.9 more girls into the mix. So what's this going to be on average?
2.7.
It's going to be, put equals 2.7 girls per bird, or per 3 birds. Which is the same ratio all along. But again, I don't want to just go straight to that, although very often, that's all you want to know very often. Very often, all you want to know is what is the average of a distribution. Quite often, quite often, quite often. But Trev still asked a great question. How do we figure out those likelihoods of each of the individuals? So let's do it. Still interested in the number of girls? And I still want to know, that was a cool noise. That sounded like something was just discovered, was it? Maybe perhaps?
Yeah.
Something discovered. I love the sound of discovery. It makes me very happy. Yes, good, good, good. It could be 0,
1,
or 1,
2,
or 2, or 3. We picked up another random variable value because we have 1 more bird. Now, what you probably noticed is the top and the bottom one, the no girls and the all girls, are the easiest ones to calculate, aren't they? Because basically, if they're all boys,
3 times 0.1.
0.1, say it a different way, Haley. It's not 3 times 0.1.
The third power.
0.1 cubed.
Oh, cube.
Right, and I that might sound like me being
Oh,
nitpicky,
I
but
was-
3 times 0.1 is 30%. That's actually too high.
I had it.
You had it in your mind visual.
I had, yeah.
So may I, if I may, I'm going to write it as 0.1 times 0.1 times 0.1. It is 0.1 cubed, of course, you learned that in your last project. But I like keeping it in terms of columns for each of the 3 girls. So you got Bertha, Nancy, and Marge, if that makes sense. You got the Bertha column, the Nancy column, and the Marge column. So my friends, there is a 1 in 1,000 chance now. There is now a 1 in 1,000 chance that you're going to have all boys. Very small. It's a very small chance you're going to have all boys. Very small chance. Notice it's getting harder and harder to get all boys.
Yep.
Originally, there was a 10% chance of getting all boys. And then it went to a 1 in 100% chance. And now it goes to a 1 in 1,000 chance. I said 1 in 100% chance. That was the wrong thing to say. It's a 1 in 100 chance, which is 1%. All right. And I think at this point, to keep things a little bit easier, we're going to jump all the way to 3. Because this is also pretty easy to calculate. Because the only way to get all 3 girls is for Bertha to be a girl, and Marge to be a girl, and Nancy to be a girl.
Cubed again.
It's 0.9 cubed, exactly. And it will always be, hopefully you're seeing the connection between this and your last project. These directly connect. These do not directly connect from your last, but that's the difference. That's why I brought this back to class, because at this point, it's too tricky, I think, to do it on your own. All right, so we knocked this bad boy down. That's 0.81. Is that 0.729?
Yeah.
Roughly 73%. Notice it's also getting harder to get all girls.
Yep.
With a flock of 1, it was 90% likely. With a flock of 2, it was 81% likely. Now it's down to 73%. It's getting harder. Because every time you reach in and grab another bird, it's like rolling a die.
Yep.
And that die can come up void. Every time you're taking a chance, which means the chance of getting them all is going down. Jada, go ahead.
I said like flipping a coin.
It's exactly flipping a coin. It's exactly flipping a coin, but instead of the coin being 50-50, it's what?
Mm-hmm.
Instead of this coin being 50, it's 90-10. It's weighted so that it falls heads up 90% of the time, heads being girl, and it falls tails up being boy 10% of the time. Thank you. That is a perfect analogy. What Jada's just done is describe what we're talking about, which is called a binomial experiment. More on that to come, as I said today and Wednesday. It's a binomial experiment. 2 things can happen, heads or tails. It's always a coin. The question is, what are the weights of the sides? If it's 50-50, it's a fair coin. If it's 90-10, it's a weighted coin. This is a weighted coin, right? Very, very much, very, very. This is what about, thank you. Perfect connection. Perfect connection. All right, you ready?
Yep.
Now, let's figure out these guys in the middle. You know what they have to add up to, don't you?
Yeah.
You know they have to add up to whatever's left. So this is 73% together. So it's got to add up to what, 27%? These 2. The question is, what are they individually? I don't know. Let's find out. Let's build 1. What should we multiply?
So 0.1.
So I got a 0.1. So now Bertha's a boy.
Yep.
What's Nancy?
A girl.
Nancy's going to be the girl?
Yep, probably.
So that means Marge has to be the boy.
That's me another boy.
Yeah.
So there's one of them. Is that the only way to have 1 girl?
No.
No, there's 3 different ways.
There's 3 different ways, aren't there? Aren't there 3 different ways to have a girl? Because either we could have Marge being, or excuse me, Nancy being the girl, and Bertha is a boy, and Marge is a boy, or we could have Bertha be a boy, and Nancy be a boy, and Marge being a girl, or Bertha could be the girl, and the other 2 can be boys. Now this is going to get really cumbersome. I'm going to pull this out of the way so you guys can see it a little better. That gets pretty cumbersome, doesn't it? You see how it's 0.1 times 0.09 times 0.1 plus point. That's very, very mathematically cumbersome. And really, it's kind of unnecessary too, isn't it?
Yeah.
Because you've written essentially the same thing 3 times. That seems a little redundant. Haley, what's the simple solution?
Mm-hmm.
What's the simple solution, friend?
Put a 3 in front.
Put a 3 out in front here.
Because you're always going to have 1 girl and 2 boys.
Good. You're always going to have 1 girl and 2 boys. The order, while important, is not important to write out.
Right.
This accounts for it. So what you just summed up, Haley, is brilliant. It's called the binomial coefficient. This number out here, the binomial coefficient, is a tricky number. It's slippery. But what's important is you have to know what it is and how to use it. So by putting that 3 there, we don't have to write out this entire sequence of numbers. And can I do one more thing, if it's okay with you guys, just to make the pattern a little more mathematically obvious? I'm going to switch the place of that 0.9 and the 0.1. It doesn't change the value at all, does it? It's exactly the same as it was, but this way you'll see the pattern kind of arise a little more naturally. Okay, what's that equal to?
0.027.
Thank you. I was going to say 0.027, roughly a 3% chance. Roughly a 3% chance of getting 1 girl and 2 boys. That doesn't happen very often, does it? It doesn't happen very often. This happens the most often. This is going to happen the next most often. We can actually figure out what that is now, couldn't we?
1 minus.
Yes. If you add up all this, we know these have to be 27% in total. This should be 24.3% if my math is correct. This should be 24.3%. And that does make sense, doesn't it? Watch this, watch this, watch this. If we have 2 girls, that means we got to have a boy with the 2 girls, don't we?
Doesn't matter what order.
And it doesn't matter what order, but we've got to account for them all. So the way I've written it right here, I've made Bertha be the boy and Nancy and Marge being the girls. But I've also got to account for Marge being the boy and, or it should say, or Nancy being the boy. Sort of slap a 3 out here again, aren't we? Now, this is why I'm happy about this. Because that by itself, without the 3, is 0.081, isn't it? That's 0.81 times 0.1 is 0.081, which is exactly 1/3 of the 24.3 it's supposed to be. So when you multiply it by 3, it actually comes up to exactly the 24.3%, which is what it needs to be to sum to 100. Yay. Yay. Yeah? Sums to 100? We're happy? Hells yeah, we are. And then we can do Haley's addition and multiplication and figure the average out. We do this guy times this guy plus this guy times this guy. This is going to start getting annoying very quickly, isn't it? It's starting to not be fun anymore. It's starting to not be fun anymore because now you're going to have more and more to multiply together and add up to get this average. Don't worry. We have a shortcut coming. And once I've tortured you guys with 4 chicken flocks, you definitely deserve the shortcut, which we'll share with you later on today. Is that fair? You guys buying this logic?
Okay.
Yes? Is it okay? Any questions so far? We're almost there. We're almost there. We're almost to my flock. Finally. Finally. Cool? Are you seeing the tie-in between all the flocks with 1 bird, with 2 birds, with 3 birds? I think. Go ahead, Elena.
Just not from here, but if I had, for example, from 0 up to 10,
Yes.
it would be the same number?
It would be the same. Hold that thought. Give me till Wednesday with that thought, okay? I don't want to jump too far. I want to go right to our flock first. Because something inevitably happens with I learned something years ago when I started using my chicken flock to not go right to 4, and you're about to see why. Going to 10 just reiterates the point even more. Hold that thought. Hold a thought. Let's go to my flock. Fine, let's add Mary into the mix. There's Mary the Delaware up there, top right corner. Is she a boy, is she a girl? I don't know. 90% of the time she's a girl. But the question is, I don't have a long run average. I've got my son holding a Happy Meal box with 4 chicks in it. So now I'm going to mute the board, and we're going to go through the motions. Actually, you know what? You guys try to build a distribution. Give it a whirl. Give it a whirl right now. I'll get it started.